That's me, as I'm committing crimes with both direction and magnitude. Oh yeah! With both direction and magnitude. Oh yeah!
I know how to add two vectors in a linear direction, but what do I do if they're at an angle to one another?
That's easy. First, you draw the vectors as they appear, making sure their magnitudes are accurate.
Next, you make two other lines starting at the endpoints of the vectors, each parallel and equal to the original vectors, creating a quadrilateral.
Finally, you draw a line going from one corner to the other, and use a squared plus b squared equals c squared to find the actual value of the net force. The longer the vector, the more force the object has acting on it. This means it will move faster.
Want to know how you can apply this knowledge to real-world examples? Well then, let's go camping.
Say you have to canoe across a river with a fast-moving current to get to your campsite, and you want to know where you should push off from to get directly across.
Here are boats in three different positions. We'll call them A, B, and C. Let's start by drawing the F current and your F paddle. Initially, it would look as if boat B would be the best choice. However, if we properly add the vectors like we showed you, boat B ends up downstream.
We now see that boat A is the best choice to get you directly across the river. This is because the combined forces of the current and your paddling cause the boat to move with a diagonal path. So if you start by paddling upwards, you will end up in the correct place on the other side.
However, if you weren't looking to get directly across, but rather for the fastest way to the other bank, boat C would be the boat to take. You'll notice that it has the longest vector, which equates to more force, meaning the boat will move faster across the river.
Another place you might encounter adding vectors at an angle is finding the tension on two sides of a rope which an object is hanging on, like this.
First, you draw the F weight pulling down on the ball. Next, you draw an equal and opposite vector for the support force going up.
Then you draw two lines, both parallel to each side of the rope, intersecting directly on the endpoint of the support force vector.
If you draw vectors going from the object to where the lines intersect with the rope, whichever vector is longer represents the greater force of tension.
You can find the exact tension on the ropes by using reverse a squared plus b squared equals c squared with the support force vector as c.
Adding vectors even comes in handy when you're moving. For example, why does a box slide down the ramp on the back of the mover's truck?
The answer is simple. First of all, there's a certain amount of gravity pulling down on the box. There's also an equal and opposite support force coming from the ramp.
If you use the trick we talked about earlier to find the net force vector, you'll see that it lines up almost perfectly with the angle of the ramp. However, the box would only really slide if the ramp had rollers or was very slippery.